Sample exercise 1. Set the working directory to sample exercise 1 folder. Okay. In this exercise, we have one assembly and one part, the ASM1 and the slider part. Let's open the assembly. So in this assembly, we have sketched some useful references. We have the path sketch and 3 points, spring end 1, point A and point B. Okay, this sketch is the curve that the slider will follow. Okay, and you can see the dimension as stated in the exercise. Okay, now the spring end 1 is one of the ends of the spring. Okay, and we have point A and point B. Point A is the initial position of the slider, and point B is its final position. Okay, now close the assembly and let's open the slider part. Okay, so it's a cylindrical part, but it will be treated as a particle. Okay, and it has a mass of 3 kilograms. Let's check it. Mass properties. Okay, and we have this point. It's on the geometrical center of the part, and it represents one of the ends of the spring end 2. Okay, now close this part and let's start solving the exercise. Open the assembly ASM1. Okay, and let's connect the slider part to this assembly. We will connect it by a planar connection, planar. Okay, and align the front of the slider with ASM front. Rename this connection to PLNR. Okay. Okay, now the slider should be or must be connected to the path sketch. For this, we are going to use the slot connection, slot, and select all this path or this sketch. Okay, then select the spring end 2 point. Okay, now let's set the limits of movement of the slider on the sketch. Minimum limit and maximum limit. Minimum limit, select this vertex, and the maximum limit, select this one. Okay, so rename this connection to SLT. SLT. Okay, now the initial position of the assembly or the initial position of the slider, drag and align spring end 2 with point A. Okay, then set the planar rotation joint axis to 0. Okay, take a snapshot and rename it to 0. Okay, now let's go to mechanism application, and first thing to do is to define the spring end 1 to spring end 2. Okay, for the unstretched length of the spring, it's equal to 0.4. Okay, and the stiffness coefficient is equal to 200. Okay, Newton per meter. Okay, so we have our spring. All right, now the initial conditions. We have to choose here the 0 snapshot position, nothing else to add. Okay, now the measures. We have two measures: the x component of the slider position coordinates and the velocity of the slider. Let's define them. We start by the x component of the slider position coordinates. New position and select spring end 2 and relative to this coordinate system, and choose here as a component x. Okay, rename this measure to position x. Okay, now the velocity of the slider, a new, and choose here velocity and select spring and 2. Rename this measure to V. Alright. Now it's time to define the analysis. Okay? Analysis, it's a dynamic analysis. We have to enable the gravity, of course. Okay? For the initial configuration, we have to choose the initial condition 1, which contains the initial position of the assembly or of the slider. Okay? Minimum interval, let's take it L.L1. Okay? And duration, take it L.75. Okay? Rename this analysis to D. Okay? Now let's run the analysis D to find out the velocity of the slider as it reaches point B. Okay? Analysis D and run. Okay? Now go to measures to see the result. Now we are going to plot the velocity V against position X. For this, use here measure versus measure. Okay, and for X-axis we are going to use the position X. Okay, graph, and zoom this region to find out the value of the velocity for which position X is equal to 0.6. Note, by the way, that position X is equal to minus 0.8 meter at the starting position, that is the zero snapshot, and will be equal to 0.6 at position B. Here is the velocity of the slider. Okay, when position X is equal to 0.6 or the closest value to 0.6. Okay, now save the analysis D. Okay, and save your work. That's all for sample exercise 1.